right, everybody, welcome to our first Hanover presentation of the spring 2022 semester. I know people are going to be joining over the next couple of minutes, but let's get started. I am actually introducing Dominik in lieu of Dr. McFarlane, who had to have an emergency surgery on his eye today. But this is a colleague and collaborator of Dave's and was nominated for this series by Dave. I'm actually going to paste Dominik's research website into the Zoom link for those who, into the chat window for those who want to learn more about what he does. But Dominik is a scientist that studies the effects of various variables on tree structure and function, and in particular has been involved with some groundbreaking 3D laser scanning technologies, and is going to share what he's learned most recently about the structure-function relationships in trees and forests with us today. Just a reminder that these are recorded for those who cannot join us, so feel free to turn your videos off if you don't wish to be in the recording. And thank you all very much for joining us. Take it away, Dominik. Thank you for being here.
Yeah, thank you for the kind introduction. Welcome, everybody. It's my pleasure to speak to you from Germany at night right now. And I will, as far as I know, we have around about 60 minutes. So I will try to limit myself to around about 45 minutes of talking. And I will talk to you about structure-function relationships in trees and forests. And I also termed it new insights from fractal analysis, because fractal analysis is basically the fundament of a lot of stuff that we do right now. And that's also the fundament for the collaboration I have with David so far. So this is going to be a key part of that. So let's start with the general idea of what kind of motivation we have to start with. And we started with the idea that tree and forest structure is closely related to the ecosystem services and functions provided by individual trees or the forest or the community. And I guess you're all aware of all those functions, and to name just a few, we have the pure production of wood, we have biodiversity, we have the regulation of gas exchanges and climate, we have the regulation of the water circulation, and we also have the scenic beauty or the recreational benefit that people have from being in the forest. And the question to address these issues that arose was basically, why is there this uncertainty in the relationship between ecosystem functions and services? So just assume some selected ecosystem function or service here on the y-axis and the structure of a tree or a forest on the x-axis. And sometimes these relationships could be positive linearly, they could be negative, sometimes they may be asymptotic, and often it's hard to generalize. And our hypothesis to start with was basically that this questionable or sometimes unclear relationships are related to the fact that we have unclear information or imprecise information on the structure of a tree or a forest. And actually that structure is what we manage. So if we have an opportunity to measure this precisely and to manage it precisely, we should also be able to then manage the ecosystem function or service we wish to have from the forest. So for that reason, we started out with addressing forest structure and tree structure. And it basically comes down to that Robert Kaplan statement that was, if you can't measure it, you can't manage it. So the basic motivation lies right there in the wish to better describe structure and structural complexity. And when we started out, we looked at the existing approaches that are out there, conventional approaches to address. And we found that the canopy lifts that people sometimes use are kind of scary, they're complicated, difficult to apply on a large scale. Hemispherical photography wasn't really providing us access to real three-dimensional data, and other approaches are just way too complicated and laborious to conduct on a larger scale, like constructing scaffolds on a tree, as you can see here in this image. However, those conventional measures are interesting, and what we usually do with it, we measure tree height, we measure the crown length, we might measure the diameter at breast height, or we measure the crown projection area of a tree. But a lot of what is really interesting is all this in here, the real three-dimensional distribution of plant material in the tree or forest, in the tree crown or forest canopy. And to get that, we explored the capabilities that are out there, or the options that are out there right now to get those information from 3D methods that actually provide us X, Y, and Z coordinates. And many of you might know the LiDAR technology, light detection and ranging, the radar technology, or photogrammetry, all of those providing X, Y, Z coordinates. However, the most promising one on a high resolution level to us was the LiDAR technology. And that is what we work with for quite some time now. And we explored there the options of ALS, so the airborne laser scanning from a plane platform, the MLS from a vehicle, as well as from handheld devices, and also the terrestrial laser scanning that is conventionally meant when speaking about those devices attached to a tripod. And all of those provide us real world 3D data. And in contrast to a black and white photograph, which you might assume to see here right now, this is actually a three-dimensional scan. So for each pixel, we have more than just the color value. We also have the X, Y, and Z position. And from that data, we have actually a perfect description of the structure of an individual tree, but also of the entire forests. And today, actually, it has become a very easy task to do this for plots on a larger scale. And what you see here is a handheld laser scanner from the company GeoSlam. This is the one that we use, but there is more on the market. And this device doesn't even need a GPS signal. It is completely independent from other sources than itself. It just needs the battery equipped, and you can walk through a stand. Let's say here we have an area of a hectare by a hectare, 100 meters by 100 meters, so a hectare in our German units here, and you would just walk through this site. This is actually the real world trajectory we see. This is why you see this kind of up and down movement in this line, because the person walking through the stand naturally has some up and down movement while walking and holding the device in the hand. And after just 20 minutes, we have an absolutely, more or less complete and precise three-dimensional picture of this entire, in this case, beech forest here in Germany. What you can see here in the front, maybe you can see it small, is a hunting seat. So the traditional German wooden construction where we just climb up a little ladder and sit in while hunting. And you can see that this gives you an impression of the scale. Actually, we have 35-meter tall trees. And as I said, this is around about 1 hectare in area, and it's just 20 minutes. So we have access to this data now. And we looked into the definitions, actually. What are the definitions of structure? And forest structure may be defined as a summarizing term describing all dimensional, architectural, and distributional pattern of plant individuals and their organs in a given forest space at a given point in time. This is maybe the most comprehensive description or definition of forest structure by McAleeney from 2005. And a tree structure may accordingly be defined as a summarizing term describing all dimensional and architectural and distributional patterns of all organs of a tree at a given point in time. And I guess you can agree with me that this is a bit bulky. So it's a bit of a lengthy description. And we were looking for alternatives, ways to get a more easy access to the complete three-dimensional distribution of all these data points that we now have in the laser scanning data. They're called point clouds. So basically clouds of 3D points describing a forest with all the details. And maybe a better way to assess that structural definition is to directly look into complexity. So the structural complexity of what we are looking at. And complexity is hardly ever described in a comprehensive way, but maybe the best one was given by Gell-Mann and Lloyd in 1996, following some of the ideas from Shannon, the famous Shannon we all know from the Shannon Diversity Index. And it can be summarized basically by the fact that the length of a description of a system or object is directly what is meant by complexity. So if we look at this very simple representation of a tree here, we see that we have a stem that can be described maybe as a rectangular lengthy object, and on top of that sits a crown here described as a circular object. And by describing the length of that rectangular object and its width and the radius of this circle, we could probably describe this tree pretty well. So it seems not to be a very complex object, since we don't need a lot of description to do a nice description, and a lot of words to do a nice description. In contrast, if we look at this tree now here, We could say it is more complex than the other one because we would need much more words or bits and bytes to describe what we see. We would have to describe the tapering of the stem, the different branching angles, the lengths of the branches, and all this kind of stuff. So maybe this description is very intuitive and actually a short definition of complexity. So it's the length of the description you can make for an object or system. And we then set out on our research goal that we want to develop a quantitative and objective measure of structural complexity that actually relies on the 3D vegetation data we have in a holistic way. So all of it, not just trying to derive the dBH or the crown length or the crown projection area, but using all of it, kind of making use of the full potential of the data now available from the laser scanning approach. So we set out with the idea that we want any point cloud to work. And if we speak of any point cloud, we can say that a mobile laser scanning point cloud should be processable just like a terrestrial laser scanning point cloud, an airborne laser scanning point cloud, or even a 3D point cloud obtained from structure from motion, photogrammetric approaches. And we want that to be processed in a software. We use Wolfram Mathematica. You might use R, Python, or C++, whatever kind of platform you want to use to process your data. And from that, we want to derive the complexity measure. So it should be something very, let's say generic, applicable to everything that is out there in different platforms that people prefer. And we came up with the idea to use the box dimension. The box dimension is a tool from fractal analysis. And here we are already in the idea of fractal analysis, and is based on the theoretical work by Benoit Mandelbrot from the 1970 years. And in that we can maybe try to grasp in a quick way what is done during the calculation of what we call the box dimension. And if you imagine this tree here, just imagine that you put it in a box. And you would say then that when this box has a given length, you need one box to enclose the entire tree. And if you reduce then the edge lengths of this box in this case here to half of the initial box, you would need 8 boxes, 4 on the ground level and 4 on the upper level to capture this entire tree or enclose it. And you would then just continue to use consecutively smaller boxes and count the number of boxes that you needed to enclose the entire tree, going down all the way to very, very tiny boxes that should not be smaller than your resolution that you have for your data. So maybe in terms of laser scanning, a few centimeters, but you can go quite small. So from the tree being 30 meters tall, a 30 by 30 by 30 meter box, all the way down to maybe 1 by 1 by 1 centimeter. And all you would do is you would oppose the length, the edge lengths of the box with the number of boxes you needed to enclose the object. And you can use a tree, but you might also use just a branch, a root structure, and an entire forest is also possible. It's all depending just on your computational power that you have available. And you would then calculate the box dimension from what is shown here. So basically, you would plot the length of the box that you used. So you use different lengths, and for each length that you use, you plot it in relation to the length of the initial box that you started out with. So basically, it's kind of a scaling factor. And you invert the axis so that basically the big boxes is on the left and the small boxes is on the right. And then you show this in a logarithmic scale on the x-axis. And on the y-axis, you just show the logarithm of the number of the boxes that you needed. And for a tree like the one I just showed you, you would get this kind of data. You would get almost perfectly straight line of points showing you basically the number of boxes needed over the size of the boxes. And in this case here now we would have the small boxes on the right. We need a lot of small boxes and just a very few of the larger boxes. And interestingly, in Benoit Mandelbrot's idea on the fractal analysis and fractal mathematics, he showed that when you look at the equation of the regression line and the R² value for this regression line, we have a lot of information given that actually relates to complexity. First of all, the slope of this regression line is what we use as the box dimension. It's what Benoit Mandelbrot described as being the box dimension, a measure of complexity that is scale independent. But it's more actually. the R² value directly relates to the self-similarity of the object. So the repetitional pattern across the different scales and sizes of boxes that we used can be described as self-similar if they are always the same. So if across scales the same structures are observed, then this value is very high. We have a high R² value. And you can do a lot with that information. But also, if we would now assume these extra points are added here, so some nonlinearity suddenly happening, Benoit Mandelbrot also said that if you observe something like that, it is likely due to scaling boundaries. So for instance, if you would oppose this data to measurements of photosynthesis, it could easily be that you would see that photosynthesis doesn't easily scale from the leaf to the forest level, because you would see some self-similarity. So he interprets that as self-similarity ends and scaling boundaries arise, and one has to be careful if that happens, because something is changing in the system with regard to the structure. And finally, also the intercept of the regression is related to the dimensionality. So while the box dimension is a dimensionless measure, this intercept gives you some idea on the overall size and dimension of the object you're looking at. And we so far mostly focused on the box dimension, but also explored a little bit into the others. But here for today, because of the time, we will just focus on what we did so far with the box dimension as a fractal parameter. Well, interestingly, this box dimension, this measure of complexity from now on, can range from 1, which would represent a simple line, or basically a stem that doesn't have any branches, a dead tree if you want, to 3. 3 would be the equivalent to a perfect cube, fully filled without any holes. And somewhere in between, you find every natural tree. So for instance, here you see a Douglas fir tree I scanned in Oregon with 1.2 roughly as a complexity value. Another tree with a little bit higher, a bit more complexity, a beech tree from a German stand. Here we have another beech tree growing more in the open. A beech tree, 300 years of age, growing in a park without any competition, developing very complex and space-filling structures, and so on. And actually at 2.72, Benoit Mandelbrot showed that you would find what is called the megasponge. The megasponge is an object that has a super large surface area, but a very, very small volume. And he called it a sponge because it has this large surface that could technically hold a lot of water capacity, or hold a lot of water, has a high water holding capacity with a very limited volume. So a very light object with a gigantic surface. It's a mathematical object that you would hardly find in real life. But it has a box dimension of 2.72 that was empirically proven. And somewhere on this axis, basically, you could line up every tree, and also you could line up forest stands. And we started out with looking at forest stands and found that, of course, depending on season, there's differences and stuff like that. But we looked into some trees here in the summer condition and forest, basically, in summer condition forest plots, 40 by 40 meters, and we saw that the complexity, so here dB is the abbreviation for box dimension, on this plot level was first of all related to the space filling. So we used the laser data to measure how much of the space was actually filled in this forest, and we could see that with increasing space filling, we also see an increase in complexity. This is little surprising, and also here the R² is actually 0.44, so round about 45% of the variation in the box dimension was explained just from the pure abundance of plant material, the space filling. This is not surprising because Mandelbrot assumed that he partly also proved that the box dimension addresses both the density and the distribution of material in space at the same time. So in our case, plant material. So around about 45 to 50 to 55%, I only ran the numbers for these plots here, are attributed to where the material is, and the rest, around about 45 to 55% of the box dimension, are related to how much material is actually there. So we have around about 50-50 share in theory, and it seems quite close to that, what we found here in real world. Then we ask ourselves the question, okay, what makes a single tree a complex object when it comes to the box dimension? So we will see here always the box dimension on the y-axis, and the different parameters of the trees, structural parameters on the x-axis, we can see here that total tree height was positively associated with the box dimension. We can see that the volume of the tree was positively associated with the box dimension. We can see that the mean crown radius was positively associated with the box dimension, so as the crown surface area, and even the branching angles of the first order branches and the second order branches seem to have some positive, bit more scatter here, some positive relationship with the box dimension. Interestingly, all those parameters can be addressed and changed by silviculture. We could also promote those parameters. And by testing that statistically, we could show that a model that combines the height, so we have the vertical extent of the tree, the mean crown radius, so the horizontal extent of the tree, and the variation of the branching angles of the second order, so those branches that really spread out from the main branches to explore space. Those three parameters combined explained the largest amount of, or were the best predictors for the box dimension, basically 73% here. And meaning basically that a large tree with wide extensions horizontally and vertical and some very good space filling is the one with the highest complexity. And that basically fits very well to what everybody would assume intuitively. We tested this for Douglas fir trees. Here we see Douglas fir trees that grow near a gap. So we have a stand gap. And those gaps were created in this young stand thinning and diversity study in Oregon. Some of you might know that, I guess, where they had Douglas fir stands cut with gaps. And in these gaps, we had trees facing directly the gap. And those trees had a higher average box dimension than the trees in the stand interior, because they had no competition and they were developing longer crowns, or keeping longer crowns. They had less self-pruning than the stand, the forest in the interior stand, the tree in the interior stand, sorry. So that also gave us confidence. Okay, we have some logical results here. We tested again for beech trees in Germany here. We tested, does a beech tree growing in a mixed neighborhood of other tree species as competitors have a different box dimension than a beech tree growing just among beech trees as neighbors? And we found that that is the case. A beech opposed to competition from other species seemed to develop a more complex crown, and that perfectly fits to what Bayer et al., for instance, found in 2013. They made this nice drawing of a beech tree here. The left one is a beech tree growing among competitors of different species, developing a wider crown and greater angles, and a beech tree growing among other beech trees, kind of making itself a lot of competition, which is, according to niche partition theory, perfectly logical, and also reflected in the complexity of those trees. We then thought, okay, what about the productivity? And we looked at, here in this case, more than 100 tree species and more than 391, or in this case, exactly 391 trees made it into the analysis, for which we tested the relationship between the box dimension on the x-axis here, the complexity, and the annual increment. And we saw that there was a positive relationship. So with increasing complexity, trees tended to be growing better. We could also show that the box dimension was a good description for the surface to volume ratio. So the surface to volume ratio here in this case means the surface in terms of the crown surface area derived from the laser scans, meaning basically the photosynthetically active outer hull of that tree, versus the volume of the wooden skeleton that was holding this tree crown. So all the wood of the tree, not the volume of the entire crown with the leaves and everything, just the wood, the naked skeleton of the tree. And we could see that this surface to volume ratio, which can be considered a measure of growing efficiency, was nicely positively correlated to the complexity level. So meaning that trees seem naturally to grow better when, or more efficient when, they are also developing more complex crowns. So we call this a growth efficiency parameter. We then thought, okay, this is all logical on the tree level. What about the stand level? And we looked at the stand level. We tested stands of different sizes here. So we have small subsections of the forest. Basically, on the left column here, you see 10 by 10 meters, then 15 by 15 in the center, and all the way up to 20 by 20 meters forest sections mathematically perfectly cut out of the three-dimensional data. And we related the complexity of these plots, forest plots or forest subplots, forest sections, whatever you want to call that, here on the y-axis, with the different parameters of individual trees being shown here on the x-axis. So for instance, here, the box dimension of the most complex tree, what is called here dB max, was positively related to the box dimension then of the plot. So we see a strong effect of the most complex individual on the plot level complexity, which makes total sense since the plot is rather small. So if there is a very complex architecture present by a single tree, then this has a large effect on a 10 by 10 meter plot. And this effect seems to diminish from 58 to around about 30% explained variation with increasing size. We also found that the sum, so the sum of the individuals in terms of complexity was positively related to the box dimension of the plot. And also the standard deviation, the variation of the complexity in the plot, has a positive effect. All of that is probably what one would intuitively expect. We then thought, okay, what about the differences between coniferous forest and deciduous forest? And we tested this on data from ALS campaigns, from airborne laser scanning, on 66 beech and pine and spruce forests. And we found that the deciduous forests in almost all cases were more complex than the coniferous counterparts. And that was also something we expected from the rather poor structural complexity you could visually see in our German pine forests or spruce forests, which are mostly really high productive monocultures. And then we thought, okay, what's the management effect on that box dimension? Can we also see that? And we looked at continuous cover forestry here on the left, CCF, even-aged forest here in the center, and primary forests, which we unfortunately don't have anymore in Germany. So we had to make these measurements in Slovakia and the Ukraine. And we measured the complexity of these plots, in this case, 40 by 40 meters again. And we could see that even-aged forests in the German management system were rather low in structural complexity, while the continuous cover forestry resulted in some quite distinct complexity, but still not on the level of the primary forests we measured, which were the most complex ones. And actually, as you can see here, with levels of up to 2.45, almost 2.45 as a mean, quite close to this theoretical value of the Mengerswand, which was 2.7. So great complexity for natural forest and reduced complexity as a result of management. There's very few exceptions here where we really have continuous cover forests that are consisting of 16 different tree species. So maybe species mixture is more a matter here than the management per se. We also looked at age classes and we saw, well, again, this confirms that this box dimension measure seems to be something useful. So from TH here, which indicates the thicket stage, to the polewood stage, to immature and mature forests, we saw an increase in structural complexity described based on the box dimension. We then thought, okay, is that really meaningful? So does it mean something on the plot level beyond that complexity seems to comply with what we visually think? And we looked again into these 66 plots here that we considered an area of 50 by 50 meters. And we compared the box dimension here always with the y-axis being the box dimension with several parameters. Maybe you all know the SCI by Zenner and Hibbs we see here in the upper right corner, the structural complexity index, which seems to correlate with the box dimension. And the SSCI here is a laser-based index introduced in 2017, which is called the Stan Structural Complexity Index. Maybe not the best name since it's so similar, but it's a different index. It's based from the 3D data, while the Structural Complexity Index by Zenner and Hibbs is based on tree position and height. We also see the relationship here with the coefficient of variation of the diameter at breast height. We saw a correlation with effective numbers of layers, which is something similar to the foliage height diversity, basically derived from laser scanning data. We see this relationship with age, increasing complexity with age of the forest. We see a relationship in a negative kind of way with the silvicultural management index. Yeah? So with increasing management of the forest here to the increasing x-axis, we see a decrease in structural complexity. And we also see that there is the diurnal temperature range here, abbreviated DTR. So the change in temperature within a day is decreasing with smaller numbers here with higher complexity, and then is the diurnal temperature range increases when the complexity of the plot drops. So even an effect on the microclimate was visible here without having several microclimatic sensors. We just had one sensor in the center, and already that sensor showed this pattern. What we didn't see in a significant way here was a correlation with a traditional parameter, the basal area. Surprisingly, the complexity of a forest does not seem to strictly correlate with basal area, which makes some sense when you think about it in a three-dimensional pattern, actually, because it depends on the architecture of the individual trees and not of their diameter. And finally, a data set that is not yet published, but even more interesting actually is when we compare the box dimension in the summer. So here I said leaf on because this was midsummer season here. We compared it to the relative annual increment. The periodic annual increment actually is that given in relative numbers for a period of 5 years. For different plots here, we have 23 beech forests that are located all across Germany. It's from a huge biodiversity project in Germany that is running for several years now. These plots have been established to cover a nice gradient of conditions. And we can see here that the complexity of these plots here from left to right increasing was closely, or at least significantly, related to the increment on the plots. And in this case, this means the increment of all the trees bigger than 7 centimeters that we measured by hand. So looking back into this range of data we had here from the box dimension from 1 to 3 and that theoretical maximum of 2.72, we might say that somewhere between the 2.2 and 2.5, somewhere in this range here, I can't pin down to the exact numbers, but somewhere here must be a hypothetical complexity optimum or maximum of an individual tree. I guess from theory, we could say it doesn't make sense for a tree to look like a mega sponge because it would result in a large amount of shading, self-shading, and that would be highly inefficient. But somewhere here in this range, obviously seems to be the maximum of tree. And we found that forest stands as a community can have a much higher optimum. Looking at the one that I have here in the figure, it actually had 2.6 as a box dimension, so very close already to the maximum value, theoretical maximum value, because obviously self-shading, in this case, it's not self-shading anymore, it's shading of other parts of the lower forest strata, but it seems to be no problem in this case. Nature seems to make use of that. And when we think about that a bit more, we might come back to the ideas of thermodynamics, and particularly the work of people that tried to apply thermodynamics to ecosystems. And we all know that processes of life, so living processes like photosynthesis, use energy, in most cases energy provided by the sun, and work with this energy for the biological processes like we do with adding carbohydrates through food, and plants do it by harvesting the light. Yeah, and then they work with this light and they try to use this energy as efficiently as possible, transforming it slowly to a lower quality energy, which in the end is usually heat. And in a paper from Nielsen in 2020, they tried to bring this thermodynamical idea into ecosystems, and they refer to Brione's cascade of a one-way conversion of energy quality, meaning that high energy quality or quality of high energy, usually in terms of radiation, is slowly converted through intermediate processes here to chemical, like adenosine triphosphate for during photosynthesis, and then at some point ends up as a low quality energy in the form of heat at the end of the day, and dissipates slowly. And during that process, the second law of thermodynamics states that entropy has to increase. So we have energy is consumed and entropy is created thereby. And there was also work done that showed that the more mature an ecosystem is, the more energy is stored in this system. And also the higher is the rate of additional energy capture. And the thermodynamic people usually then refer not to energy, but to exergy, because they split up energy into exergy, the usual usable part of the energy, and an anergy, which is basically the unusable part, the static energy that is in an object due to its position, for instance. But exergy is still usable. For instance, sugar could be considered such a usable energy source. And they interpret this as higher exergy level. So if the storage of exergy in the system is high, we have a high buffering capacity. So the system has energy stored that it can actually use to deal with outside effects, for instance, disturbances. And this buffering, or this adaptive capacity, as probably many people will consider it, of an ecosystem, may be one of the most important ecosystem resources of the future. So it's very interesting that we might be able to address that through fractal analysis by looking into the box dimension of a forest, describing thereby its buffering capacity. So if it's more complex, it is likely also able to have a higher adaptive capacity. And we all know the work from Püttmann and Messier and Coates referring to structural complexity or complexity itself as a tool to manage the adaptive capacity of a forest. And Jorgensen in 1992 developed a scheme for that, and it was also recited here in Nielsen, where they showed that their idea or their hypothesis of how this relates. And we could see here that exergy storage, so the available buffer capacity, is much greater in a mature ecosystem. So we could say in a primary forest, when compared to an immature ecosystem, let's say a young plantation or a primary forest right after a major disturbance. And that can be translated into buffer capacity, which is extraordinarily interesting, because maybe this is the future challenge, is to make use of the buffer capacity and maximize it as best as we can. So as a take-home message, I guess we can say that fractal analysis provides new insights on the causes and effects of structural complexity in trees and forests. We've seen what makes an individual tree complex, what makes a forest plot complex as a combination of trees. And we can also say that the management for this complexity, as we all want to promote, basically, due to the recent developments in silviculture in general, that we all acknowledge this as an important parameter during silvicultural management, that we should strive to have complexity. We can now put it on solid grounds, because we know from these 3D data that there is a way to maximize it. We can run analysis and run simulations in order to provide a pathway how to maximize the complexity of a given stand, or to minimize the loss in complexity during harvesting and silvicultural approaches. And also this resembling of natural complexity, or mimicking of old growthness, can be justified then based on thermodynamics. So the application of thermodynamics kind of indicates that the natural high level of complexity is directly related to the buffer capacity, and this is really something we want from our forests. And therefore it is maybe justifiable now, what often has been hard to justify. And with that, I would like to thank you for listening. I just see we have some extra time for questions, and I'm interested to hear your ideas and questions regarding what I just presented to you. Thank you very much.
Thank you, Dominik. Thank you so much for a wonderful talk. So I'm just jumping in. If you have any questions, this is the time to ask.
Okay. Does anybody have a question? You can also use the chat. I'll check on the chat as well. Yeah, there is a question. Just go for it. I guess you don't have to raise your hands, just shout it out.
Sure. that was a really nice presentation, super interesting and kind of exciting to see how that technology is coming along. And I may have missed this. I had a grad student in and out a couple of times. Has anybody applied this to try to quantify impacts of forest pests in terms of canopy damage, either on an individual tree or even within a stand?
Yes, we do a lot of that right now based on not really pests, but the effects of the tree dieback because of droughts. And I know that some colleagues of mine do some work regarding some caterpillar infestations that eat all the leaves. So they monitor the effects of that leaf loss basically during vegetation period. They see this decrease in leaf abundance or leaf presence basically, but that's all I am familiar with when it comes to pests.
Have you done that with the handheld lidar device?
The handheld lidar is not precise enough for that. It has a resolution of roundabout, well, it would be precise enough if all the leaves are gone at some point, of course, but if you want to see some smaller leaf damage and some small increase in canopy openness maybe under the tree, then I would recommend the terrestrial, the tripod-based laser scanner, because the tripod-based laser scanner is just much more high resolution. It's just better for that purpose.
Oh, very good. Thank you very much. Enjoyed that.
Any other questions?
Yeah, I think Aki had a question. So do you know if any similar work for root structure?
Sorry, with which structure?
Root structure.
Oh yeah, well, root structure has the ultimate limitation that we cannot scan it, right? So there is the georadar technology that allows to capture the coarse roots, the really large roots, but there is no tool yet to scan the roots in situ. What we did is we dug out the tiny trees and blew off all the sand and ground and then scanned the roots as they are hanging basically from a clamp mounted stand where the tree is fixed, and scanned that. And we could see that tiny roots are a problem because they are fairly close to the minimum size an object should have to be scanned with the devices that we have. But also we could see that they're completely out of their natural structure when they are blown away from the dirt around it. So scanning them in situ is still a big challenge, and I'm not aware of any approach there. What has been done is X-ray technology. I think that was done by I can't recall the name right now. It's a fellow from the US actually that she did X-ray scans from roots in some kind of substrate that is easily penetratable for the X-ray, and scanned tiny roots in situ, but that's all I'm aware of. It's just a methodological problem still.
Okay, so Rich has a question. Rich, would you like to ask that question, or should I read it from the chat? So Rich has a question. So can you provide a simple intuitive definition of a box counting dimension?
An intuitive definition. Well, I guess the best way to describe that is it is a measure of the amount and distributional pattern of material in space across scales. So if you have an object that is completely self-replicate across scales, like you use a filled cube, then every smaller cube resolution you pick would result in you observing a filled cube somewhere in this bigger filled cube. But as soon as there are some holes or some what is it called in English? The opposite of the filling, basically. You start to make this cube look like the mega sponge. You create holes in this cube. You have changes in that pattern, and the box dimension basically quantifies how much is there and how is this distributed. That's what it does at basically two things at the same time, which is an advantage. It is something holistical. It's something we haven't had before, but sometimes it can be hard to interpret because you just get a number, you get a single value, right? Between 1 and 3, and you don't really know what caused this value. So that's why we spend so much time on trying to figure out what makes this box dimension larger and what makes it smaller for a tree and for a forest. I hope that answers the question. Okay, thanks.
So we have another question from Giorgio. Any hypothesis on why the natural forest trees had more complex structure compared to managed forest in one of your graphs? Is it due to different competition conditions?
No, we actually assume that, or there is quite some good evidence for the assumption that nature actually optimizes that space filling. Natural processes, all the plants with all the photosynth sensors that decide on where to invest for new plant material, to explore new space and to reach out for light. When you let these processes take place in a natural manner, they naturally develop to maximized complexity, because the maximized complexity is immediately related to maximized efficiency. And that efficiency is what the plants obviously seem to strive for. We could call it the goal function of a forest community in a natural condition is maximizing light capturing with minimizing the investment to do so. And whenever we humans start to do silvicultural approaches, which is absolutely fine because we want to use wood, but whenever we do it, we have to be aware that we are affecting this perfectionalized natural system in a way that probably the only function we optimize then is the timber harvesting. We can optimize the straightness of the stems and stuff, but we will never optimize the structural design of the whole thing, because the structural design encompasses more than just the productivity of wood. This is basically not something a tree is particularly interested in, growing a particularly large stem. It's just interested in growing as efficiently as possible to survive. And I think that's the reason why natural forests are just more complex than anything we normally have in our management systems.
So we have another question from Rich. So is there any evidence that box dimension varies with shade tolerance? Is it greater box dimension with greater shade tolerance, or vice versa?
Well, at least we could see that shade tolerant species have a tendency to be more complex. Yes, that's true, because they seem to cope better with the effects of high complexity in the crown, resulting in a higher shading of themselves. And also we've seen, we published that also, that there is a dependency of the perfect or the optimal complexity for a tree depends on where the tree grows in terms of latitude on the planet, because the solar angles play a big role here. And if you are a tree growing in the boreal, like a Christmas tree, you have no benefit from growing like an umbrella, because the sun never shines from above you. So it always comes from the sides, and therefore the tree tries to optimize light capturing by growing more like a Christmas tree, while a tropical tree with a lot of sun coming from the top, from high solar angles basically, has a lot of benefit from growing like an umbrella. And we've seen and shown that this is still visible in trees, even if you grow them all in the same area. And the genetic building code still tries to kind of optimize for what the trees had in their home habitat, in the home territory. So it's hard to say. The general shade tolerance level is directly related to the complexity, but we can say that the more shady the conditions are in general, the more tolerance, so the more shady the conditions a tree usually can stand, basically, the more likely it's also a very complex tree or species. Are there more questions? I guess we still have like 10 minutes. Seems not to be the case.
Thank you so much, Dominik. It was a great presentation.
You are very welcome.
I think Renee and Emily already have told you that this is recorded, and then we'll we'll post it and send you the link as well. And
Yes.
thank you for agreeing out invitation and then just presenting your work.
Thank you very much. Well, then I guess it's time for me to go to bed now. It's 10:30.
What time is it? Is it now there?